Yes, I would like to thank the organizers, first of all, for setting up meeting in this beautiful place and for giving me the opportunity to speak. I'll talk about another instance of holography, ADS-CFT, where we actually do have a hope to solve things exactly and completely. And well, this is just the basic duality between n=4 superrank-mills and strings of the ADS5 cross S5, which, as we know, is an integrable system. So it manifests itself on the weak coupling side if we interpret the dilatation operator as a quantum spin chain. This quantum spin chain turns out to be integrable, and it can be solved by beta ansatz. On the strong coupling side, the scattering theory on the wall sheet of the string turns out to be integrable, and I mean, its S matrix satisfies all axioms of integrability. And again, one can apply the machinery of integrable systems to figure out what happens dynamically. And actually, one can bootstrap what happens in the middle at any coupling and understand ADS-CFT at the quantitative level in any coupling regime. And it works beautifully for the spectrum, but it's a general truth about integrable models that it's always possible to understand the spectrum. Whatever integrable system you take, there are some sort of spectral equations that you can write, and it will be beta ansatz, or I don't know, Y system, or there is a very efficient tool, specially tailored for ADS-CFT, that's known as quantum spectral curve, which describes the spectrum of the theory, which, because it's a CFT, it's this spectrum of scaling dimensions. But if you go to correlation functions, even in simple integrable models like, I don't know, Heisenberg spin chain or one-dimensional Bose gas, it's still very much work in progress how to compute them. The correlation functions are difficult. And also in ADS-CFT, well, there are proposals, but there is no final theory that would compute you any correlation function at any coupling strength. So I'll talk about an instance where actually, from general knowledge about integrable models, we expect that such exact description should exist. And this related to D-branes, or defects in conformal theory. So you may consider a D-brane placed in the bulk, well, if it happen to end on the boundary, that would produce some sort of defect in the dual CFT. A D-brane is an endpoint of open strings, and potentially it will break integrability. So even if excitations of the string scattering among themselves elastically, and the rest matrix satisfies all the Young-Baxter equation and so on, the boundary itself may break integrability because the reflection of the boundary may create particles, and the boundary conditions need not necessarily be consistent with integrability. So there are a set of requirements that the boundary conditions should satisfy, and if you are lucky, then the D-brane itself will be integrable, and then one, in principle, can apply usual integrability bootstrap in this setup. So what can we compute then? Well, the ingredients in principle are known. So the basic ingredient of an integrable field theory is an S matrix, and there is a known expression for the S matrix of ADS CFT that was derived by Bizart many years ago. So the boundary introduces an extra scattering factor because an excitation can reflect off the boundary, and for the integrability to be preserved, this reflection has to be elastic. But it can change quantum numbers, so it is described by a matrix with two indices of incoming and outgoing states. And there is a certain set of consistency conditions between the S matrix and the reflection factor. If they are satisfied, then the system will be integrable. But these conditions are typically so strong that you can find that they more or less uniquely fix this matrix and the boundary reflection given the symmetries of the problem. So they can be basically found from integrability bootstrap. So these are the ingredients, but then it is known from studies of integrable quantum field theory that given these ingredients, one can actually compute universally an basic quantity that characterizes a boundary of the string worldsheet, which is just the boundary entropy. And this is defined by the partition function on a half-infinite cylinder, so that, it will have a bulk piece, which is basically given by the ground state energy. So if you think of this direction as time, this would be the usual Boltzmann factor. But then the prefactor will depend on the circumference of the string, and this is known as the G function in statistical quantum field theory. And if a QFT is integrable, then there is a generic method or idea how to compute this function by through thermodynamic beta ansatz. So if you go to ADS CFT, then what is the physical meaning of the boundary entropy? So this would be the worldsheet of the string that ends on a D-brane, and then the other end of the string should end on the boundary. This is kind of a natural thing for a string to do, that it will approach the boundary at infinity. And this other endpoint describes a local operator. So the states of closed strings are due to local operators in the dual CFT. So this will describe a one-point function of this operator in the presence of the defect. So since defects break conformal symmetry a little bit, we assume that they don't break it completely. So for instance, scale symmetry is still there, but translations in the directions perpendicular to the defect are obviously broken. And then one-point functions are allowed. So they are not zero, and this is the simplest response function that one can imagine in the presence of a defect. And in the integrable situation, this should be proportional to the G function, or just given by the G function of the dual string theory. So generically, the defect will indeed intersect the boundary at a line or a point or two-dimensional hypersurface and so on. And so in that case, it will describe a defect conformal field theory, where this would be a line defect, or a point defect, or a surface defect, or and so on. The D-brane can also go parallel to the boundary, and in that case, it describes the situation where the gauge symmetry is fixed or it's spontaneously broken. So this corresponds to Yang-Mills theory going onto the Coulomb branch. Or it can end on the boundary at 2 points, and this corresponds to inserting some heavy probe. For instance, it can describe a 3-point function with 2 operators being very heavy and 1 operator being very light. So all of these setups corresponds to D-branes, and they can be studied in some sense in a uniform manner. But as usual in integrability, there is no plug-in formula, so one has to study each case anew. But the techniques are similar, and the architecture of the formulas one gets are also similar. Okay, so in string theory, D-brane, well, it's either a surface on which open strings can end, or you can think of it as a surface which it can absorb closed strings. So in integrability, this is also these two dual descriptions. They are mutually interchangeable, and both are important and convenient to use. So one can either think of this as a theory on a half line, so this time direction now goes in the vertical direction, and space is half infinite, so the world sheet ends at some point. Or one can view this horizontal direction as time, and then vertical direction as space, and then this would be a world sheet of a closed string that emerged from a D-brane. And in this case, the D-brane is described by a state, by a particular state in the Hilbert space of the closed string. So the question is how to characterize it from an integrability point of view. And this was, there is a well-known paper by Goshal and Zamolodchikov from 30 years ago that sorted out this question in full generality. And basically, the idea is the following. So in this open string picture, integrability condition requires that reflection of the string modes of the boundary are elastic, so there is no particle production involved in the reflection process. So if there is one particle that approaches the boundary of the string, it can bounce off with the same momentum, and it cannot produce a pair of virtual particles. Virtual particles it can produce, but it cannot produce other on-shell modes, and it cannot change the momentum, only the quantum numbers. So if you view this in the cross channel, then this state at the boundary will consist of pairs. So it will be a coherent superposition of paired particles with opposite momentum. So the state will be, roughly speaking, given by this. So this will be a collection of paired magnons with opposite momenta, with some weights, which at this level are not fixed. And so, in this sense, integrable states are those that have this momenta paired. Or sometimes people formulate this as a condition that the state is annihilated by all odd charges of the integrable hierarchy, because odd charges are odd functions of momenta. And so if all momenta are paired, then obviously they are equal to 0. And this is a very strong condition, actually. It's, if you take a random boundary state, it will not satisfy it. It's not very easy to find such states. And interestingly, ADS-CFT produced a huge stock of these states that were not known before. So people studied them in condensed matter context, but then the study of motivated by N=4 and string theory, they produced a new sets of new classes of boundary states that were not known. Okay, so in this language, the one-point function is an overlap of a boundary state with a given on-shell state of the string that is dual to some operator on the boundary. So it's characterized by some quantum numbers at the position where this operator is inserted. And the question is how to compute this overlap. So there is a remarkable result in the theory of integral systems that this overlap, and with it the one-point function in the defect CFT, always has a very rigid structure. So it's basically given, well, there is a dependence on x, of course, is fixed by scaling symmetry, but then the dependence on kinematics is encapsulated in what is known as Gadan matrix. This is basically a Jacobian of beta equations. So for integrable boundary states, the overlap is always the square root of the Gadan superdeterminant multiplied by some prefactor which has a very simple dependence on momenta. And basically, this prefactor is the boundary reflection phase in which the reflection is diagonal. Okay, so how much time do I have? For this to be too abstract, let me give one example. This is based on recent work with Charlotte Christensen, and it has to do with 't Hooft loops. So 't Hooft loops are it's a typical example of a defect operator that exists in any gauge theory, in particular in N=4 super-Egg Mills, and it is a disordered type defect. So it is not fixed by some operator that you insert in the vacuum, but rather by boundary conditions that you give to the fields in the path integral. So, so basically what it does, it inserts a point like monopole of Dirac type. So it's an abelian monopole at some particular point in space. So its evolution with time covers a line, so it's a line defect. And then, so this field of the monopole is the boundary condition that is fixed at the origin, so as R is going to 0. Now, in N=4 super-Egg Mills, one may or may not add a scalar, but if one wants to preserve supersymmetry, then one better adds a scalar condensate in addition to this gauge field one. And then this defect will preserve some part of supersymmetry. And also, if you don't add the scalar, it may also be, it will require a normalization, so it will not be even conformal. Anyway, so for this supersymmetric defect, it breaks part of conformal symmetry, but not all of it. In particular, dilatations are still a part of the game. So it defines a codimension 3 defect CFT with all the consequences for the operator algebra and for correlation functions that one can constrain using basic CFT tools. So the dual description is a D1 brane in the bulk. So if the 't Hooft line is a straight line, then this will be embedded as ADS2 in ADS3, and it will be a point on the 5 sphere. So the point is characterized by this vector that also defines the scalar condensate. And it was known for a long time that the boundary conditions for the string of this D-brane do not break integrability. So we do expect, well, this, strictly speaking, this only tells us that integrability is preserved at strong coupling, but while having a good faith, we may expect that this will also be true at weak coupling, or at any coupling, essentially. And then we may expect that we will be able to compute exactly the one-point functions using more or less conventional tools of integrable models. So I will tell you how to do it at tree level, but for arbitrary operator. So let me just show you how to do it at tree level. So so first of all, what are we actually calculating is just a constant, because the dependence on the distance is fixed by scaling symmetry, and this constant can be also viewed as an operator product coefficient of a small 't Hooft line. So if you take, we can always map a line to a circle, and if you view the circle from very far away, then the correlation function, the one-point function, will be determined by, obviously, by the same coefficient. Since, well, there is an extended object somewhere near the origin, and we probe it from far away, this is basically OPE. So the 't Hooft line is expanded in the powers of its size with the operator coefficients, and this operator coefficient is I think we need some cheer up, no? So this is so these numbers are OP coefficients of the circular 't Hooft loop, which we expand in local operators. Then the question is how to calculate them. Well, for protected operators, they can be actually extracted from localization. Here is the formula. I will not tell you how to derive it, but we did it. One can presumably do it very directly by localizing in the presence of the 't Hooft line, but we did it using S-dualities, so we can map this problem to a correlator of a Wilson line, for which the answer was known from the work of Akuyama and Semenov and myself. And then, so invert the coupling and take the large N limit, and then we obtain this very compact formula, which is actually exact. So it is non-perturbative in lambda, and if you expand it in the power series in lambda, it has finite radius of convergence as expected from planar perturbation theory, and indeed one can check that the first two terms is just classical contribution, where we replace all the fields by their classical values. And then the first correction is when two of the fields are connected by a propagator. And there is actually a very beautiful theory of how to quantize in the presence of magnetic monopole that goes back to the work of Dirac in the 30s. And so one can use this monopole theory of monopoles to find the propagator in the presence of the 't Hooft line. And indeed, everything works beautifully. This reproduces the localization result. At strong coupling, well, one can get even a simpler answer, and one can reproduce it by integrating now the propagator in ADS, so whose one end is sitting on the boundary, the operator insertion, and the other end is integrated over the D1 brane. So that also reproduces the expected result with all the coefficients. Okay, so but if we want to compute a one-point function of a non-protected operator, then a priori we don't know how to do it, apart from just using Feynman diagrams. But integrability can help, and so in that context, it is convenient to think of operators as spin chains. So for instance, if you consider an operator built of scalars, then this will be characterized by a wave function of an SO6 spin chain, which is integrable, and its spectrum can be computed by beta ansatz. So by solving a system of beta equations with three types of beta roots, because the symmetry group SO6 has rank 3, and the beta equations are completely characterized by the group theory data, by the Cartan matrix, and the highest weight of the spin representation. So solving this equation, we can find all the states and all their one-loop anomalous dimensions just algebraically from the beta equations. Okay, so then if you want to compute the correlator of this operator with the 't Hooft line, at the leading order, we just substitute the fields with their classical values. And in the language of the spin chain, this projects the state, given state characterizing the operator onto a state with particular components at each side. So in a sense, we are just picking one particular component of the wave function where the spins are aligned with the vector that characterizes the 't Hooft line at every side. And so one needs to compute this overlap for a given state. Now, integrability by itself and beta ansatz produces an expression for the wave functions of the states, but they're not really useful. In fact, to compute them, so if you want to put it on mathematically, it's easy to diagonalize the Hamiltonian as a matrix. So the beta ansatz expressions are sums over permutations of lengths that is given by the number of excitations. So they grow very quickly in complexity, and it's just meaningless to use this expression in computing the overlaps. But this state turns out to be integrable. So it does satisfy this selection rule that it only projects into paired states. So if the state is characterized by n magnons, the overlap will be 0 unless these magnons are paired. That for each rapidity we have the state with the opposite, with the rapidity that have an opposite value. So the state must obey this Z2 symmetry. So if it does not, then the overlap will be 0. And we know that for these integrable states, the overlap should have a universal form in this determinant representation. So for this particular state, actually this representation was already known. It was derived by Deleuve, Gomberg, Christensen, Leonardopoulos, and Poshguy. But if it were not, it's very easy to just, well, if you know that the answer has this form, guessing this prefactor is super easy. You need to compute an overlap with just one state. Well, so this produces the answer that is valid for any state whatsoever, well, to the one loop accuracy. And presumably there is a generalization of this formula to all loops. What one needs to find is how this prefactor is modified, because the Gadan part stays the same. So one can also do the same game with the operators that contain derivatives. Let me maybe skip this part. So, here one needs to use the formula that was derived by Legendre in 1785. Basically, the boundary state will be linear combinations of Legendre polynomials. So linear combination of all states of the spin chain, and here the Hilbert state at each side is infinite dimensional. So potentially the boundary state can be arbitrarily complex, but what we get is very particular coefficients that are given in terms of Legendre polynomials. And quite remarkably, the integrability condition for this state is basically boils down to the recursion relation for Legendre polynomials. So this state is also integrable, and indeed it has a very simple overlap expression, again in terms of Gadan superdeterminant and some prefactor depending on the Q functions of the state. So this was more for an illustration, but there is by now the whole list of defects that turn out to be integrable. And in some cases, the answers are known even non-perturbatively. For instance, for D3, D5, a CFT that describes domain wall between the vacuum with different gauge groups in n equals 4, or for heavy light correlator. There are also some results for domain walls in ABGM theory and for the Hooft loops, but so far they are only one loop exact. So there is still some work to do here to find a fully non-perturbative description. So there were, very recently there was veritable progress in ADS3 as CFT2 duality related to integrability. To the best of my knowledge, D-branes there have not been discussed, which to me looks a bit surprising, because in that case there is an interpolating parameter that brings, so it's basically the amount of the Ramon charge in the background. One can dial it to 0, and then string theory is described by conventional worldsheet CFT, and well, there studying D-branes is a very classic topic in string theory. On the other hand, integrability is, by now, is also well understood, so one can apply similar techniques to study also real Ramon backgrounds. Also, for the 't Hooft line, it's very natural to combine integrability with the bootstrap, which was done for the Wilson line so far, with great success. And I would expect that for the 't Hooft line, it will should also work in parallel, because it's a one-dimensional DCFT and one-dimensional CFTs are simpler. There's only one cross ratio, for instance, in the 4-point function. So this would be a natural playground to also extend the bootstrapability approach. So with that, I would like to thank you again, and thank you very much.
Thank you very much, Kostya, for this very nice talk. Are there questions for Kostya? Yes. Oh, there are a couple. Let's do Boris and then Zoli.
Thanks. Just a very short question. So in n equal to 4 super Yang Mills, just like you need a choice of representation for Wilson loops, there's also a choice of representation for 't Hooft loops, presumably?
Yes.
So
yes,
were
yes.
you just computing the one-point functions for a 't Hooft loop in the fundamental, or could you generalize?
Yes, yeah, this is the simplest. We were doing the simplest case, which is, so for the, yes, Wilson loop is characterized by, you can say, by Dinkel labels and numbers. And the 't Hooft loop is characterized by n charges of the monopoles in each of the Cartan vectors. So we considered the simplest ones, which have only one charge, and it's elementary, one allowed by 't Hooft
Principal integrability holds for the whole set of them.
Yeah.
So you showed this formula for the overlap, which contained the superdeterminant and products of factors in the ADS CFT before. So
Yes.
this is valid only for large operator, no? Or
Indeed, yes.
yes, and can you prove this formula, or why is it a product?
I thought you proved it.
No, actually, recently we analyzed this 't Hooft loop, and we found that it's not always a product form.
Well, there can be linear combination of this type of formula. So this is the building block. This is what you mean?
No, it depends actually on which grading you do the calculation, and in some grading it's a product form, in some other grading it's a more complicated expression.
Aha, that's interesting. You should tell me how.
Yeah. Another question. You mentioned some exact formula for this BPS Wilson loop, and then you showed that there is one piece which is a wrapping correction.
Yes.
So I was a bit wondering, because this is a supersymmetric object, and I would believe that the wrapping should be 0.
Why?
Because fermions and bosonic contributions should kill each other.
No, but this is in the non-trivial vacuum in a sense, right? So the operator itself is BPS, but then you couple it to a D-brane, which is sort of orthogonally. It's also supersymmetric, but the supersymmetries do not completely match. So the one-point function is non-trivial, right? So it's
yes.
a full-fledged function of the 't Hooft coupling, and it contains wrapping and everything. It's the same for D3, D5.
But this is an exact formula what is on the screen. So no more correction, this is exact.
It's large and exact.
Yes. Okay, I will think.
So in view of time, I would say that we can thank Kosti again.